So this is lesson 3.2. We're going to look at the infamous or famous cathode ray tube experiment and the plum pudding model.
All right, the first objective is to recognize the significance of the cathode ray tube experiment to the development of the atomic theory.
And then, hand in hand with that, we're going to be explaining the new and improved plum pudding model of the atom that came out of the cathode ray tube experiment results.
And then reading 4.2 in your packet for this material if you would like to read it on your own.
And you can stop at the end of the section about the cathode ray tube. We'll cover the Rutherford nuclear model in the next lesson. So our time frame right now, is about the mid-1800s.
All right, well, I got that wrong.
And early through the mid-1800s, Dalton came up with his theory in the early 1800s. And for the next couple of decades, people basically were accepting the idea of Dalton's atomic theory. And to review Dalton's 5 points of his atomic theory, matter is made of atoms was the first one, and they're tiny particles.
Yep, made of atoms.
And the second one is that atoms are indivisible, which means there is nothing smaller than an atom. They can't be divided or split into anything smaller.
Spell indivisible. There we go. I'm good to go. Indivisible.
Okay, and then atoms of a given element are identical. So all the atoms of hydrogen are alike. All the atoms of oxygen are alike.
Are identical. There we go.
Are identical for a given element. And then he went on to say that atoms of different elements are going to be different in their mass and other properties.
Different. Or do that.
Different elements are different.
Different
atoms.
Different.
Okay, and the last part of his theory is that atoms combine with one another to form compounds, and they always do this in the same relative amounts. So atoms can be combined to make
form
compounds.
Compounds.
And what we're going to look at today is the next kind of major advancement in the discovery, and it's going to affect the one that Mr. Hunter's circling right now, the fact that atoms are indivisible. So the experiment we're going to review is going to call that part of the theory into question.
All right, next slide.
So in the mid-1800s, scientists began to experiment with passing electricity through things. And they found that if they forced electricity through a tube filled with gas, the gas began to glow.
Well, who was this person, by the way, before we get too far?
This gentleman we're looking at there with the lovely mustache is J.J. Thompson. He was a professor in England.
I think he's a physics professor.
Physics professor.
I think he's actually a chemist, but a lot of chemists consider him to be a chemist now.
And so the device he was using, we have a little schematic of it here, and they called it a cathode ray tube, or CRT for short. So the way the cathode ray tube worked is, on the left side, you see what is known as the cathode, and it's a negatively charged metal plate, and that's kind of inside of this glass.
Inside a vacuum as well.
Yeah,
well, not
a small amount of gas.
Yeah, small amount of gas in the vacuum.
Okay, and then down here, the next two metal discs are the anode, and that would be the positively charged part. And what Thomson was experimenting with is if you cut little slits in the anode, these greenish rays that seem to emanate from the cathode, some of them would shoot right through the slits and pass straight on down the tube. And they actually coated the far end of the tube with a phosphorescent material that when these rays, that they were calling them, struck, they created a glow in the phosphorescent material.
Yep.
So he actually won a Nobel Prize just for kind of working that out.
And then he took it one step farther. I don't know if it was him or one of his predecessors, one of his students maybe, who went on to do the charged plates. I think it was him.
I'm sure he had people working with him.
I think it was him. They have two plates. They had two differently charged plates. They had one plate that they had as a positive charge. They kept above it, and then another plate that was negatively charged.
And they wanted to see how these particles, or rays, as they called them, would react to the presence of an electric field with a positive charge. And you can see this second dashed line indicates that when they turn the voltage up on those plates A and B, What happened, Mr. Hunter?
Well, I drew it backwards, so we're going to go anti of what the drawing currently has. So when they turn it on, these negatively charged, I'm now drawing in blue, particles shot through what it did before, but then it met this positively charged plate, and it started to deflect, and what it did was basically
So the glow moved to a different location.
move
there.
up to here. So our
And of course, you said these particles were negatively charged. They didn't know what they were at the time, but
they
what
proved it.
evidence
They
do we
found
have?
out it was negatively charged because it was attracted towards the positive plate. So that's
they
something
already
you want to make
knew.
note of.
Opposite charged particles attract one another.
The cathode rays were attracted to the positive,
To the positive metal plate, which
Yeah.
indicates they had a negative charge.
yeah,
And as far as we know,
opposites attract.
light and waves like that don't have charges. So, but matter does have charges.
Yes.
Things made of matter. So these rays that they thought were like some form of light, this is very strong evidence that these are actually some kind of tiny particles.
Tiny particles, yep.
So that was groundbreaking, to say the least.
Yeah, I mean, the next thing he did, so he had one gas they tried, and then they went on to try a different gas. And when they tried that different gas, they found that, so let's say they did helium, they got this result where it went through and bent up as well. And then they went on, and let's say they did argon next, and when they tested argon, argon did the same thing.
Same exact
And then they
result.
went on and tested neon. I mean, the guy didn't stop after 2, because in science, 1 point a plot does not make. So, they tested many different
Every
gases.
gas they could get their hands on.
And every gas behaved the same way. They all went from being this neutral gas to having this, particle that became attracted to the positive plate and would hit over here. So every gas had that exact same characteristic.
So now we're seeing a trend that this seems to be something that's common to all matter.
All matter. Yeah, they couldn't get some matter in there. I mean, solids really are hard to vaporize. So
But everything they tried
worked out.
had this result. So that was pretty profound. And then when he did the mathematical analysis, which we're going to cover next, came the real startling thing.
All right.
So what did Thomson do with his results?
Well, the first thing we did talk about was the fact that the particles that were being produced from the cathode were being attracted to the positive plate. So that's the first thing that he interpreted from his results, that these little particles were negatively charged.
Negative.
So
So
they
cathode
made
rays
small, or he made small, negatively charged particles. And Mr. Fergus, what did we go on to name these things? He went. Well, he doesn't think he named them, but someone else.
I think he did name it.
You think he did name them?
Yes.
What did we
But
name
the
these?
next thing that he found was, or he called them electrons.
Yeah, so these things are known as electrons. He discovered electrons, and if you see Mr. Ferguson and I write something that looks like this in the future, that is shorthand for electron.
That's the universal
so,
symbol, a little e with a negative charge, which is basically what an electron is.
yeah, so get used
Now,
to seeing that when we're writing.
Being a physicist, J.J. Thomson began to look at
the math.
the math behind it, like how much
charge he applied to those
charge
plates.
he applied to those plates and how much deflection it caused. And he was a great, math whiz, and he was able to backwards calculate then, if I applied this force of electricity across those two metal plates and the particles deflect a certain amount, he was actually able to determine what the mass of those particles must be.
compared to
this is
hydrogen.
the shocker.
Or helium? Hydrogen.
This is the shocker. At this time, the lightest known element was hydrogen. And
Yep.
as far as if we follow the Dalton theory that atoms are indivisible, tiny particles,
There
a
should be
hydrogen
nothing
atom was
smaller.
the smallest thing there was in the universe.
And now he comes along and
What
he
did
does
Thomson's
this.
math show about the
Yeah,
mass
he
of an
said that he
electron?
found a particle that was approximately 1/2000th the mass of hydrogen. So right there, he threw Dalton's theory for a tailspin because he just said, hey, hydrogen's not the smallest particle anymore. So either he discovered a new element or
Right,
he
a
just...
new element that was 2,000 times lighter than anything we ever
Yeah.
saw, or the way Thomson chose to interpret it is, since he found the same particles coming out of every different gas, there's a tiny negatively charged particle inside all atoms.
Yep, so he thought it
So
was a...
now atoms suddenly aren't indivisible, atoms are divisible. They have parts. I think divisible has an I at the beginning. D-I-V-I-S.
I know, I could. It was supposed to be part of the D,
Okay.
thank you.
Okay.
So it's not divisible.
It's divisible. Atoms are divisible. They are definitely divisible.
Mr. English teacher over here making fun of my handwriting. What?
D-I-V-I.
Oh, really? Really? I don't like you anymore. I hate spelling.
Telling it like it is, man. Okay,
The fact
atoms
that
are divisible.
Going
Okay,
there.
they are divisible, so that part of Dalton's theory was gone. And now, let's use a little reasoning here. We know that atoms are electrically neutral, which means they don't have an imbalance of charge. They have no charge, no net charge.
Exactly.
So if you can make negative particles pop out of something that's neutral, by reasoning, what else has to be in there?
Oh, you have a neutral species overall. There has to be a negatively charged species that's attracted to the positive plate, and then something else in there to not make it an overall negative charge.
Yeah, because if the atom was just full of electrons, it would be highly negative, and it's not. It's neutral.
The world would be very repelled.
So there must be something positive inside the atom too. So atoms have charged parts.
Positive,
They have positive and negative parts.
negative parts. This again
And again, the
took
atoms,
for Dalton's theory and just took a sledgehammer to it. He said, well, we took a part of his theory and took a sledgehammer to it and said, sorry, it's no longer divisible, and there are smaller parts than atoms. So
instead of saying, well, Dalton must be right, Thomson, you're a wacko, scientists looked at his data and said, this is pretty convincing, we need to change our model of the atom. We are no longer going to visualize atoms as indivisible spheres like marbles. They've got parts inside them.
exactly. So let's take a look at what that would look like, or how Thomson interpreted it would look like.
So you're going to want to take a minute, maybe pause the video, and draw the model that we have on the screen.
So draw a sphere, draw a circle, and then little negative circles with negative signs in it, and then little positives all around it without little circles around them like they have here.
And J.J. Thomson, being from Britain, they're big on a dessert called plum pudding, which is sort of like a sticky cake with a bunch of raisins in it.
Sounds absolutely
And so
horrible.
it's nasty, but they like it over there in England, and he called his model of the atom because it kind of resembled a plum pudding, the plum pudding model. I call it like the raisin muffin model.
I like
You can
chocolate
picture it
chip
like
cookie
that.
instead.
Chocolate chip cookies are flat though, and the one thing we want to keep in mind is, even though we're showing it flat on the screen, it really is supposed to be spherical. So, however you want to look at it, it's the negative blue circles
are the electrons, as they have labeled, and then the sphere or a cloud or the pudding portion is what he interprets as kind of like a positive mush. If you're thinking of like a chocolate chip cookie, it would be the dough. If you're thinking of the plum pudding, it's the pudding. If you're thinking of the bran muffin that you were talking about, it would be the muffin
part.
And the little raisins inside would be the negative. So he just had all these little negatively charged particles that he thought you could rip out by doing his cathode ray.
If you put enough energy into it, you knock some of those
and every
electrons
element in the known to man at this point had that same property. So everything had a negatively charged particle and a positively charged.
And there's enough positive
cloud.
in the dough to balance the negatives and the electrons, and it all works out to a neutral atom. And so that's what basically visualized that the mass was equally distributed, like the dough is equally thick throughout the atom. They knew the approximate size of an atom was around 10 to the minus 10th meters on that scale, and the dough went
Also known as an
evenly across
angstrom for people who are curious. I believe that's an angstrom, right, Mrs. Gasparini?
I believe that is.
Okay, she just showed up. That sounds I'm talking to her.
Angstrom. It's like
it's
a
like
A
one
with an
angstrom.
angel,
Yeah. One
arrow.
angstrom. It's a unit that we don't use
Rarely
much
use
anymore.
anymore. But so this is the plum pudding model. So make sure you note that the positive charges in the dough, the negatively charged electrons in the spherical,
And it replaced the fact that it was a solid sphere model that was indestructible to now a plum pudding model where it's completely rip-apartable.
And let's also write on there that the mass is equally distributed throughout, because I think that's going to be a key point.
Yeah, that'll be a key point later. Equally distributed.
So it's equally dense throughout the atom.
All right. I think that covers everything for this one.
Plum pudding model.
We will see you for the next one, which I think's Rutherford, right?
We're going to move on to Ernest Rutherford.
He'll be next one. All right. Have a good night.
Save that.
And here are the PVQs. Go ahead and answer these the best of your knowledge using the information given, and we'll cover them in class the next day.
Okay. See you then.
See you.